Hi, the video for Tuesday's class is going to be split up into 3 chunks that are 25 minutes each. And this first one is just going to be a review or a redo of what we did last Thursday, because I didn't record that when we were on Teams. So if you feel like you really understand the base N notation, then you can just skip this one and look at the other two, right? So the starting point for base N notation was thinking about the meaning of what our place notation is with ordinary base 10 numbers. If I have something like 1, 2, 5, 4, as the positions of these digits mean that some of them are more important than others. The 1 up front is in the thousands place. The 4 at the end is only in the units place. If I write this thing out with the meaning of place notation, it's this: 1 times 10 to the third power plus 2 times 10 squared plus, what else, 5 times 10 to the first power, and finally 4 times, well, you could write it as 4 times 10 to the 0, but I most often leave that off. I do want to point out, though, that remembering that this is the 10 to the 0 spot helps you with realizing that this one is the third power, not the fourth. See, there's 4 digits here, but we count the positions 0, 1, 2, 3. All right. And of course, you can do the same thing with other numbers in place of 10. This is just an artifact of human beings having 10 fingers, I think. So I believe the example I gave first in class was base 5. Let's do a different one here. If I did base 7, then I could have numbers like 621, and you put a little subscript on it to mean that it's base 7. 621 base 7 means 6 times 7 to a power plus 2 times 7 to a power plus 1. I just didn't write the powers because I wanted to get it to the end and remember 0, 1, 2. Okay, so those are the first and the second power here. That maybe isn't necessary with just a 3-digit number, but I find that doing the process that way of leaving the powers out at first and then filling them in as we go back sometimes helps me. All right, so that's sort of what place notation means. If you're in an unusual base, the digits are actually multiplied by powers of that base, and you can just work this out as an ordinary number, right, as a base 10 number, and get an answer on your calculator. In other words, this form of things lets you convert from some funky base to base 10. The question of how to convert in the other direction from base 10 to some unusual base like this is a little tougher, but not much. So think about how, I've just made a comment here that the place notation lets us change a base 7 number to a base 10 number. If I want to go in reverse and take a base 10 number and get a base 7 number, I use the repeated division algorithm. So we did an example, I think at least one example of this in class. My whole point here is to kind of review what was done in class. I just want to point out something about remainders. If you took this 1254 number, 1254, and you divided by 10, what would the remainder be? It would be 4, right? Because all these other pieces have 10s in them. There's 10s because of the powers of 10 in the other digits, or in the other elements that correspond to digits. But the 4 on the end is by itself, so this is 1250 plus 4. That means it's 10 times something plus 4. That's the remainder. What's the remainder of 621 if you divide by 7? Very similar thing, 6, 7. We get that 1, because these other things have a 7 in them already. So the point then is, the point of me pointing that out is this. If you divide a number by 7, figure out what the remainder is, that's going to get you the units place. So repeated division, the first step is divide by the base. Started to turn the H in the into a B there. Weird. Divide by the base. And the remainder, I just abbreviated that remainder, REM. The remainder is going to be your units digit. So that's a place to get started. When you first divide by the base, whatever you get for the remainder is going to be your units digit. But the rest of the digits work the same way. You just take the new quotient you've got and divide by the base again. Let's run an example. One of my favorite bases playing this kind of stuff is base 12. Because honestly, it's because when I was a little kid, there was this Schoolhouse Rock video called Little 12 Toes that I thought was really funny. And it's about doing base 12, which it weirdly works, even though it's for, like, you know, third graders. You get across the basic notions of base 12. And it's about this, like, alien guy who has 6 fingers on each hand. And so it's natural for the aliens to do base 12 arithmetic. I'll just mention one thing. The digits that we normally have, 0 through 9, they need some additions. You need single digit things to represent 10 and 11. Those are the possible remainders when you divide by 12. And in Schoolhouse Rock, they used dec and L. They call them D and E, or a little delta and epsilon, I think. So those are going to be your digits. 0 through 9, and then dec and L. So let's try to convert a number into base 12. How about if I give you 145 as a base 10 number? Cool. Well, let's see. The process is this. You take your 145 and you divide it by 12. 12 goes into that 12 times. You notice 144 is right before that. Multiply back, you get 144. And then, of course, 1 is the remainder. So 145 base 10 is equal to something base 12 that has a 1 in the units place. I'm going to fill in the space here with the rest of the digits. So that's one division. We're supposed to repeat that. And what you repeat is dividing the base into what the last answer is. It's a little weird that they're both 12s right now, but we'll divide 12 into 12. And we'll get 1, of course. And 1 times 12 is 12. And so the remainder you get is 0. Am I supposed to write a 0 here now? Yes, I am. But it seems confusing, like getting 0. Should this be the, should you ever start a number, the leftmost position in a number be 0? I don't think so. You know, if it was a 0 in the leftmost position, why bother writing it at all? So I guess we're not done. Yeah, and in fact, that's right. Getting 0 as a remainder, that shouldn't surprise you. Sometimes digits will be 0 in the middle of a number. But getting 0 as the answer, that is the quotient, that is something that's a little unusual. And that's the condition that you know you're done with. So let's do one more division. It's 12 divided into the previous answer, which is 1. That goes in no times. And so the last remainder that we get is 1. So this is the full set of digits for 145 base 10. It's 101 base 12. I thought it might be nice to do one more example of that kind of conversion stuff. So just a little bit longer. 1711 is the number I chose, which I think works out nicely. But that's a base 10 number, and I want to convert it to base 12. So 12 into 17, wait, yeah. I guess I'm going to need a calculator for this. 1711. I think I can probably manage to show you the calculator on the GoPro here, and oops. Hopefully this will work out that you can see the process we're doing. All right, that's pretty good up there. So take your 1711 and divide it by the base 12. Try to center this better. Okay, you see what the answer is there? I can't read it right. 142.583. Well, 142 is your answer, and in fact, your remainder is hiding there in the decimal digits, in the stuff out to the right of the decimal point. So I'm going to subtract 142 from the previous answer. And you see now by doing that, I've just gotten the decimal stuff. Well, that's something over 12. So just times it by 12, or whatever you're dividing by, and it tells you what the remainder is. So let me collect that up here on the whiteboard. We've got the answer was 142, and the remainder, I don't even need to know what this number is. The remainder was 7. I got that from the calculator. Okay, now I feel guilty. What's 142 times 12? 1704 is what would go on that line. And is that right? 11 minus 4 is 7. Yeah. Okay. So then that means the units place digit is 7. Let's keep going to get the other positions. So 12 into 142. I think that goes 11 times. 11 times, shoot. 11 times 12 is 132. That's right. So this goes in 11 times. Multiplying back, I get 132. And then that's a remainder of 10. Now, when I have a remainder of 10, I've got it. That's when I need to use my single-digit things that represent base 10 numbers. 10 is going to be a little D thing, deck. All right. One more time, I think. 12 into 11. Well, it doesn't go at all. You get 0 is the answer. That's how we know we're on our last digit. And of course, that means 11 itself is the remainder. But we won't write 11. We'll use that single-digit number, L, or 11. Just remember that we got these digits in reverse, right? So this is really L, dec 7 as a base 12 number. Now finally, we're going to take a look at the 2 or 3 unusual bases that get used in computers. I did a shtick about binary finger counting in class. I think I'll skip that for the recorded video, but binary is certainly the first thing to talk about. Let me just count in binary for you. 0, 1, 2, 3, 4, 5, 6, 7. That's probably enough to get the pattern. These numbers could be parts of a byte in a computer memory, and so if you did have 0 as the meaning of the thing, there's actually other digits in that byte. So I'm trying to give a rationale for why we might do the following, which is if something's a little short, pad it out so that it has the same length as the other guys. Pad it out with other zeros if necessary. So 000, 001. Now these guys are all the same length, and there's a handy thing going on here. This takes a little foray into computer science history. You guys are probably most familiar with computers that have either 32 or 64-bit widths. That is, words in those computers are that long. And typically when you have 32 or 64, you actually break them up into 8-bit bytes. So you're used to bytes having 8 bits, aren't you? Well, in the early days, they didn't. They had 6. And 3 and another 3 would be a way to get 6. So you could, back in the 60s and maybe the beginning of the 70s, find systems that had 3-digit binary things next to one another, so 6 binary digits, and you could abbreviate those using the octal digits. So these 8 binary 3 tuples are corresponding in a nice way to the digits that you get in octal, which are 0 through 7. And the place where this still is seen actually are in the permission systems, the permission identifiers on a Unix system. So in Unix, the access permissions for a file are divided into 3 things: the user himself, a working group that user is a part of, and anyone at all in the world. And so for each of those, you'll have one of these triples. So the triples represent read, write, or execute permission. So you just read them across. RWX means, well, 000 would be a terrible permission thing. It means you're not allowed to read it, you're not allowed to write on it, and you can't do anything with it. Well, actually, maybe it's not. If you had something that was intended only for the user, you might give them the ability to do these other things, but the group and the world would have 000 on it. So the way these permissions actually get expressed is to give a triple of octal numbers that will give you a read, write, and execute for each one of those groups, or user, group, and world. Let me give you a quick example. Suppose you wanted the user to be able to do everything. The group, we'd like them to be able to read and execute, but not write. Writing on it might mean they changed the script accidentally. And the world, suppose we just didn't want to give them anything, so no permissions. Then the permissions on that file would be 750. I know that right away because 7, that's all 3 bits are on. 5, that's 101. Right? So that's read and execute, but not write. And world, nothing, is just 0. Okay. So a very common permission code you'll see is 755, for instance. It means the owner of the item can do anything with it. The group and the world have to be able to read and write, but not to, read and execute, but not to write. Sometimes the owner recognizes that he doesn't want to let this thing be executed, right? So, in fact, maybe nobody should be executing the thing if it's a file that could have a potentially dangerous outcome, right? If you had a script that might clear the whole disk, right? You wouldn't leave that sitting around with anybody having execute permission. So in that case, 644 would be a great permission. That would be 6 is I can read it and write it, but I'm not going to execute because I'm afraid of it. It's a nuclear bomb of scripts. 44, that's this one. They can only read it, no writing, no executing. Okay. All right, so that's a bit of a foray into a side issue, isn't it? Octal as a mathematical construct is represented by writing digits in this span, 0 up to 7. So there'll never be 8s, there'll never be 9s. How about 106? You put a little 8 subscript on it. Now, if you're in the computing world, there are a lot of ways to identify that you've got an octal number. Probably the most common at this point is to write a 0. I'm putting a dot in that so you know it's a 0, followed by an O, and then give your octal digits. So a 0, a lowercase o, I better be more careful about this so nobody mistakes it. That first thing is a 0. That little thing is the letter O. And then your 3-digit number. So that's how it's most typically in other. There are some languages that do other things, like just starting with a 0 is not uncommon. I think starting with an O is not uncommon, but this is getting to be the thing that people see the most often for a way to specify a literal octal number. Okay, for octal, because of this correspondence between the digits and binary triples, you do a lot of your conversion work by just creating this table, and it was quick. Did you notice how quickly I was able to produce that table? And you just do a table lookup. So this number 106, for instance, in binary, it's 1, which is 001, 0, which is 000, and 6, which is, where's that? That's 110. So binary is great for the other computer science bases because it acts like a lingua franca. You can translate things to binary and then translate them to the other. Okay, hexadecimal. I've got binary written up here. I didn't write octal above it, and now I'm about to move on. But this column right here is where we're doing octal. Hexadecimal is more common, seen more often in the computer world now because of what I mentioned before about the size of bytes. 8-bit bytes are very conveniently divided into 4-bit items, and I think it's amusing that the typical name for those 4-bit items is nibbles. So there's 2 nibbles in a byte. And so a nibble is a 4-bit binary string. And it's probably not so bad. I think I can quickly write down all of the binary 4 tuples. Just up front, how many will there be? Well, maybe I already kind of telegraphed that, didn't I? There's going to be 16 because that's the hexadecimal thing. So 0, 0, 0, 0 to start, 0, 0, 0, 1, 0, 0, 1, 0. Okay, I'm going to stop talking and just write them because that's faster. Here's where I said I was going to stop talking and I can't stop myself. When we're in binary, the digit 1 is the thing that acts like 9. So that 1, 1 is like a 99. The thing after that is a 100. Anytime you have something that ends in a 9, the next thing will end in a 0 and we'll bump up the next position. If we've got 2 of them, then we'll have to carry and we end up bumping up the next one after any string of 1s. All right, 0101, 0110, 0111. Now we've got like 999 on the end, so the next thing will be 1000. Then, here's an interesting thing to notice. You now have a 1 followed by 3 zeros. See, embedded in this this binary 4-tuple list that I've been creating, do you see the binary 3-tuple list, the octal numbers in there in the rightmost 3 digits? Well, what we're going to do next is see the same sequence of digits again down here. Do you see how that's going to be 1 with 1 after it, and then we'll have 1 with 10. So just a whole other copy of these triples. These ones out front remain the same, and I'll just go ahead and finish filling it out. Wow, I just made it. Well, so for octal numbers, we're going to use the numbers 0 through 9, and then letters after that. So the first bunch of things, I think I just, my memory of what I just said came back at me and said, I think I said octal. I didn't mean that. These numbers are hexadecimal. So binary, hex, just that in there. 0, 1, 2, 3, 4, 5, 6, 7, 8. 8's a nice checkpoint because it's 1000 in binary. This is 9. When you hit 10 though, that would be a 2-digit number, so that's where we switch over to using letters. And people usually use capital letters for octal. Said octal again, didn't I? People usually use capital letters for hexadecimal. So 0 through 9, then A through F. Those are your digits. I always like to point out that A is a great spot to kind of reset things and remember where you are, because A is 10. Really, it's the letter that stands for a decimal 10, and its binary representation is 1010. It's kind of cute, right? The other good point to remember is that F is all ones. F is 1111. So if I have a hexadecimal number, oh, by the way, hexadecimal numbers, if you're writing them in sort of the math world, you might say something like A109 and put a 16 subscript on it. If you're doing the same thing in a computer, or writing a string that it will be interpreted as a literal hexadecimal number, you write a 0 up front and then an X, and then the digits. I always stick with uppercase, but it's I believe every modern system will recognize either upper or lowercase for the letters. And in certain circumstances, you won't even need to see this. Like, for instance, the color specifications in HTML, they just have the digits of a hexadecimal representation. That's probably a good place to close this out. If you start up an HTML document, and somewhere in the middle of it there's the body tag, not the middle, sort of near the end of the beginning of it. A really common modifier people will make on the body of an HTML document is to change the background color. So you probably have seen this before. BG color equals, and then you'll have a hexadecimal representation. Let me give you an example of it. FF0077. These, you think of them in pairs, so there's FF is one pair. That first pair is the red content of the color. The next one is the green. And the last one is the purple. I just said purple because this is going to be purple, but it's blue. RGB. Okay, so that means full on red, no green content at all, and about halfway in blue. A mix of red and blue, more red than blue, so this would be a reddish purple shade. That's a great use of hex, because what's going on there is each of the hexadecimal digits is a binary 4-tuple, in other words a nibble, and then so each pair of them makes a byte, and what we're doing is using a single byte for each of the color intensities. All right, so that's the end of a quick review of what we did in class last week. If you've skipped this, you're not hearing me talk right now, but the next videos are going to be about sections 1.1 and 1.2.